Before we build cities among the stars, we'll build factories on the moon, our first real step from Earthbound to interplanetary. Building tomorrow's industry under an alien sky. It's one thing to dream about gleaming starships or bustling Martian metropolises, but before we ever get there, we'll have to master the far more humble art of building useful things off Earth. Otherwise, we're forever paying an invisible yet immense tax on every product we loft into the void, tribute to the tyrannical rocket equation, which demands staggering amounts of fuel just to send up tiny payloads, and even more to land them on another world. On top of that, anything we build on Earth has to be sturdy enough to withstand our gravity, making it bulkier and heavier, and tough enough to survive the punishing gauntlet of atmospheric exit at blistering speeds needed to reach orbit. There's only so large or delicate we can make such things. So every kilogram of material we can mine, forge, or assemble in a place with low gravity and no atmosphere saves us dearly, and each lunar weld or extrusion brings us one bold step closer to truly opening the final frontier. A satellite I build on the moon from structural materials made there does not need to be able to survive Earth's gravity or a high-G launch through Earth's atmosphere, just the gentler conditions on the moon, and later in space, making it cheaper to build and even cheaper to launch than the already immense fuel savings from launching from the moon as opposed to Earth. We also still benefit from the ready access to materials, the advantage of gravity being on but weak, and the huge, cheap shooting materials that make a populated industrial base on the moon appealing. While an industrialized Mars is popular in science fiction, humanity's first true space factories aren't likely to rise on some distant red planet. They'll be planted firmly on the gray, ancient plains of our moon. There's something poetic, even eerie about that. For countless millennia, the moon has watched over us as a silent witness to our triumphs and tragedies. Now we stand on the cusp of turning that familiar beacon into the site of our first alien worksites, where the hum of machinery and the glow of welding arcs will write a new chapter in its long history. Because, make no mistake, the moon isn't just a stepping stone, it's a proving ground. Before we can hope to become a multi-planet species, we'll have to show we can build and maintain complex industries beyond our protective atmosphere, in an environment utterly indifferent to our survival. That's why these early lunar industrial parks aren't merely about making oxygen or processing metals, they're about proving that we can thrive under an alien sky. Why the moon? Advantages and challenges. When we talk about building humanity's first industrial parks beyond Earth, the obvious question is, why start with the moon? Well, as it turns out, our old cratered neighbor has quite a few perks that make it a prime candidate for off-world industry. First off, there's proximity. At roughly 250,000 miles away, the moon is just 3 days' journey by rocket, practically next door in cosmic terms. That means quick transport times and near-instant communication, a logistical dream compared to Mars or the asteroid belt. It can feed our orbital industries, and it's close enough that direct oversight is possible for automated industries too. Then there's gravity. The moon's surface gravity is only at 1/6 of Earth's. That's low enough to allow us to build enormous structures that would buckle under their own weight here, yet still strong enough to keep things settled on the ground without floating away in microgravity. It also means moving heavier loads is vastly easier, and more importantly, launching them off the surface becomes almost laughably cheap. Which brings us to two of the moon's greatest future advantages, lunar mass drivers and lunar space elevators. Mass drivers are essentially giant electromagnetic railguns that can hurl raw materials, fuel, or manufacture goods straight out the moon and into orbit, no rocket needed. Given the moon's weak gravity and lack of atmosphere, these could be relatively modest installations compared to anything we'd attempt on Earth. We did a whole episode on mass drivers versus rockets, explaining exactly how these would revolutionize shipping costs and supply chains across cislunar space, along with our more recent Nebula exclusive Mass Drivers on the Moon, which deep dives this specific option and goes into more of the technical bits in math. Another option we did a whole episode on is the Lunar Space Elevator. I'm still on the fence about Earth geospace elevators being practical, but for the Moon, they're relatively straightforward. Unlike Earth, where the enormous gravity well demands near-mythical materials to support a tether, the Moon's low gravity means we could build an elevator to one of its Lagrange points using materials we can manufacture today or in the near future and on the Moon. It would allow us to haul cargo up and down at a fraction of rocket costs, turning the Moon into a true hub of space industry. Again, we've got an entire episode on lunar space elevators that breaks down just how feasible and transformative such a project could be. Once you're in orbit of the moon, it's only a bit over 2 kilometers per second of delta V to get back to geostationary on Earth, and less from the Earth-Moon L1 Lagrange point where a lunar elevator would leave you, though in fact most space elevator systems extend the tether further and offer you quite a lot of delta V to head off into space or close to Earth. The delta V from the Earth-Moon L1 to the Earth-Sun L1, which will be of interest to us later, is only a couple hundred meters per second. This delta V can also be achieved by solar-powered ion drives, since acceleration is less of an issue here and sunlight is constant away from planets and moons. While we think of space as dark, it's basically eternal daytime there. There's just no air around for light to bounce off of to give an appearance of sky. And let's not forget the moon's natural environment, which also has no sky. With no atmosphere, there's no weather to corrode the machinery, no storm to tear up infrastructure, and no pesky biosphere to contaminate sensitive manufacturing processes. Its vacuum and frigid darkness can actually be a boon for certain kinds of metallurgy and semiconductor manufacture. Of course, this isn't exactly a planetary paradise. The moon batters us with unfiltered solar radiation and cosmic rays. Its surface temperature swings by hundreds of degrees between day and night, and that fine, clingy lunar dust is notorious for infiltrating seals and machinery, abrasive enough to wear through spacesuits and jam delicate gears. But even with these challenges, the moon offers an unmatched blend of closeness, gentle gravity, and rich resources that make it the logical first step for building humanity's industrial foothold in space. And who knows, a century from now, we might look up at the familiar face in the sky and think not of romance or folklore, but of welders' torches and bustling export docks, busy feeding the rest of the solar system. Foundations. What does a lunar industrial park look like? A lunar industrial park might seem like science fiction, but the earliest versions are likely to be surprisingly humble, at least at first glance. Picture squat modular factories nestled into shallow trenches or buried under thick layers of regolith for shielding. These pressurized workspaces would hum with the sound of pumps, robots, and human crews inside, safe from the vacuum and radiation outside. Power would be a mix of large solar farms, ideally placed on the moon's peaks of eternal light near the poles, which see near constant sunlight, and compact nuclear reactors to keep operations running through the 2-week lunar night. Storing heat in thermal wadis is also an option for nighttime power generation, as is beaming energy down from orbit, particularly as providing materials for orbital power satellites for Earth might be a major industry there too. Cables would run between facilities, alongside rugged rover tracks and possibly even early magnetic levitation lines or cableways, shuttling materials and finished products from one site to another. Maintenance hubs would be critical. Expect garages packed with spare parts, robot repair bays, and 3D printers churning out replacements on demand. That's likely to include 3D printed habitats too, as that's likely to be an easier pathway than trying to locally source a broad spectrum of building materials and components, even when that might create a better product. Packed regolith, perhaps layered around inflatable structures, will likely be the first bulk-produced material on the moon, aside from fuel or oxygen. We'll get to those more in a moment, but all three along with basic metal production are your low-hanging fruit and make it possible to bring in workers and other personnel, or even families. It's tempting to handwave all of this onto robots, since they could be remotely controlled from Earth with only minor lag, but truly autonomous systems that can handle every contingency are still well beyond us, and if we had them, our entire economy back on Earth would already be so transformed that affording a manned moon base would be trivial by comparison. Only with human-level AI could we dispense with people entirely, and at that point, we'd have bigger worries than lunar payrolls, like whether our machines pose an existential threat. Over time, these hubs would expand into sophisticated depots, stocked with everything from replacement circuit boards to new pressurized modules ready to swap in when older ones wear out. The entire industrial park would likely grow in modular fractal fashion, each new cluster of workshops and smelters built with the output of their predecessors, using as little Earth-source material as possible, especially heavy, low-value items. This creates an ecosystem of production that becomes more self-sustaining with every lunar sunrise. Early candidate industries. The moon's industrial revolution won't start with building giant starships, It will begin with far simpler yet crucial industries that prove we can work beyond Earth. Construction and ISRU, in-situ resource utilization. As mentioned, we'll probably first learn to build with what the moon gives us. That means sintering regolith into tough concrete blocks, fusing it into glass for domes and lenses, or 3D printing entire structures from lunar soil. The European Space Agency has already experimented with using microwaves to bake regolith into sturdy bricks. Each successful print or cast gets us closer to habitats, roads, and shielding made entirely off Earth. Metal extraction and manufacturing. Next comes the metals. Processes like molten regolith electrolysis can extract oxygen, vital for life support and fuel, leaving behind valuable byproducts like iron, titanium, and aluminum. These can be turned into beams, struts, pressure vessels, or fine additive manufactured components, all without ever needing to haul heavy metals up Earth's gravity well. If necessary, you can produce thermite-like fuel from these too, though water ice is better, and as mentioned earlier, ion drives might be more commonplace in the cislunar economy. Fuel production. Lunar poles hold deposits of water ice. Cracking this into hydrogen and oxygen provides rocket fuel for landers, orbital tugs, and deep space missions. Even dry regolith yields oxygen that, combined with imported hydrogen, gives us a local propellant stream. Fuel depots on the moon could dramatically lower the cost of moving cargo around cislunar space. Solar shade production. One of the most ambitious early industries might be building vast, ultra-thin solar shades, whose thinness and reflectivity lets them do their own station keeping at a semi-stable place like Lagrange points. See our episode on statites and ligites for more on such fuel-free station keeping devices. These ligite solar shades, or mirrors, can be positioned at Lagrange points to help regulate sunlight reaching Earth or future habitats, specifically the Earth L1 Lagrange point to cut down on sunlight, or even specifically invisible but warming infrared light that reaches Earth. Indeed, you could use it to add more visible photosynthetic frequencies, enhancing biomass planet-wide while cutting down on infrared that simply warms the planet. You can use these to cool Venus, or vice versa. This technique can be used to warm Mars or light parts of the moon when they are dark. It is their use in climate and weather manipulation on Earth that is their big initial selling point as a Kickstarter industry for the moon, though. Imagine deploying a fleet of aluminum films only a micron thick, covering equivalent area to 1% of Earth's cross-section, probably made of mini tiny mirrors forming an invisible cloud in front of the sun, but they might mass around 3 to 4 million tons, doubled when you factor in control systems and structural supports. With periodic replacement, we could need hundreds of thousands or even millions of tons manufactured each year, especially if it's simpler to make them thicker, maybe even millions if they need to be thicker or just easier to make that way. That is nothing compared to modern Earth metal production, but it implies thousands of tons of production daily on the moon. Producing them on the moon, where aluminum is abundant and launch energy is minimal, makes far more sense than hauling them from Earth. It's a perfect early example of an export-oriented lunar industry with truly planetary significance. We were talking about early candidates to boost industry for the moon, what we might build there to take us into the future, and it is worth remembering that performing science itself is a pretty enormous industry. I suspect we'll see a lot of chemical and biological laboratories wanting to work not just in microgravity, but low lunar gravity too. But it's also a reminder that our modern society is very wrapped up in science, both financially and in terms of prestige, and both those are very powerful and common motivators for potential scientific misconduct. That's something we see in one of our largest scientific controversies of modern times, involving medicine, biology, Nobel Prizes, congressional hearings, and more, all presented in thoughtful detail in 17 pages, a new Nebula original. We see how bias, ambition, and politics can shape even our most trusted truths. 17 pages weaves together historical analysis, science, and investigative storytelling to unravel a scandal that shook the scientific and medical communities to their core. Watch 17 pages and more only on Nebula, where every episode of SFIA airs early and ad-free, along with dozens of our Nebula exclusive episodes and more exclusive content from other creators, including Nebula originals like 17 pages. Use my link, go.nebula.tv/IsaacArthur, to get 40% off. That's just $36 a year or $3 a month. Scan the QR code or click the link below to start watching now. The moon's real economic destiny is not in producing trinkets for Earth. It's in making the kind of mass-heavy bulk products that are cripplingly expensive to loft out of Earth's gravity well. Lunar factories could churn out the structural frames for satellites, shades, or vast sheets of solar panels destined for orbit, or even kilometer-scale habitats and rotating rings that would be laughably impractical to build on Earth. And of course there's the simplest and most universally needed product of all, propellant. Fuel is the lifeblood of space operations, and topping off in a lunar depot saves an enormous amount of energy compared to hauling every last drop out of Earth's deep gravity well. A moon teeming with electrolyzers cracking water into hydrogen and oxygen, feeding fleets of tankers, could become the gas station of the inner solar system, at least until the vastly superior reserves of the outer system become accessible and steadily produced enough to allow potential decade-long low-energy transfers that bring in ices from the moons of Jupiter and Saturn to replace lunar ice. And it doesn't stop there. As we refine our capabilities, the moon starts looking like a natural staging ground for truly colossal projects. Those immense solar shades we discussed, delicate yet planet-spanning, might be just the beginning. Think of sunward-facing power collectors beaming energy across the void, giant telescopes assembled from lunar aluminum and glass that could dwarf anything we've yet launched, or modular trusses stretching thousands of kilometers, serving as the backbone for future megastructures. Bit by bit, these lunar industrial parks evolve from humble ISRU plants and foundries into bustling export hubs, shipping out the raw skeletons of a solar civilization. Each girder or tank that departs the moon is a kilogram that didn't have to fight Earth's crushing embrace. Each shipment makes it much cheaper to build habitats, shipyards, and eventually entire cities in space. The moon thus becomes more than humanity's first extraterrestrial factory floor. It becomes our springboard, catapulting us from being a single planet species into one that truly inhabits the solar system. Economic and strategic drivers. Of course, none of this happens in a vacuum, ironically enough. Economics and politics will drive these lunar ventures every bit as much as engineering does, and right now, the balance sheets are starting to tilt in favor of off-world industry. Thanks to companies like SpaceX slashing launch costs with reusable rockets, moving cargo to orbit is no longer the bank-breaking endeavor it once was. The same trend that makes it cheaper to haul satellites up also makes it more viable to ferry equipment to the moon, or bring high-value lunar exports back to Earth's vicinity. As costs keep dropping, the old argument that it's too expensive to ever build real industry on the moon starts looking outdated. Then there's the national prestige and security. Being the first country or coalition to establish a robust lunar industrial base means more than just bragging rights. It means setting the norms, standards, and shipping lanes of tomorrow. The moon could easily become the new high ground, economically and strategically, shaping who controls critical resources like helium-3, water ice, or simply the capacity to build massive infrastructure without asking Earth's gravity for permission. Private investors aren't blind to this either. Many see the moon as a low-risk proving ground before tackling asteroid mining, a place close enough to Earth for oversight, but alien enough to develop the tools, techniques, and autonomous systems we'll one day use on far-flung rocks. Lunar industry is the training camp for the solar system's grand extraction game, and whoever masters it first will be well positioned to tap the truly staggering wealth of the asteroid belt. All told, lunar industrial parks represent a kind of strategic insurance policy. They give us options to expand, to secure resources, to protect Earth's environment by shifting heavy industry off-planet, and to ensure no single power monopolizes the road to the stars. In that sense, they're not just factories under an alien sky, they're humanity's first real stake in a multi-world future. Near-future projects and proposals. Of course, all of this grand lunar industry doesn't spring from the regolith overnight. It starts with humble seeds, many of which are already sprouting. NASA's Artemis program, for instance, is more than just a series of crewed landings. Its longer-term Artemis base camp concept is all about field testing power systems, habitat modules, and ISRU techniques that could evolve into the first genuine industrial park. China, meanwhile, is advancing its own ambitious plans for a permanent lunar foothold through the proposed International Lunar Research Station. This isn't some tiny outpost. It's envisioned as a sprawling complex hosting joint missions and experiments, very much with an eye toward resource extraction and technology demonstration. Europe is looking to keep pace with its Moon Village concept, which pitches a multinational, open participation settlement. It might start as a patchwork of modules contributed by different countries or companies, stitched together on the dusty plains, a collaborative quilt of industry and research. Private players aren't waiting around either. Companies like iSpace and Lunar Resources want to be the first commercial outfits prospecting and processing lunar materials. Blue Origin's Blue Moon lander is designed to drop hefty cargo loads onto the surface, exactly the kind of logistics backbone early industrial sites will need. Meanwhile, smaller companies like Astrobotic and Intuitive Machines are gearing up to make regular payload deliveries, setting up what could become the first true freight lines between Earth and the Moon. Piece by piece, these scattered efforts lay the groundwork for everything else: the power grids, fuel depots, machine shops, and smelters that will one day turn the Moon from a barren gray rock into humanity's first offshore factory, orbiting 250,000 miles from home. And once that's in place, it's hard to imagine we'll stop there. The long horizon, the Moon as Earth's industrial park and beyond. If these early factories and freight lines succeed, what follows could be truly staggering. A century from now, the Moon might look less like a desolate gray ball and more like an intricate necklace of lights, dotted with mining pits that glow at night, railguns flickering as they launch cargo skyward, and domed habitats strung together in sprawling settlements. It's the first real taste of O'Neill's high frontier, that grand vision where the Moon becomes Earth's quarry and workshop, shaping up the raw materials that orbit will turn into rotating habitats, vast power arrays, or even shipyards building the interplanetary freighters that will connect us to Mars, the asteroid belt, and beyond. Cheap raw materials combined with the Moon's natural vacuum could unlock manufacturing processes that are impractical or outright impossible on Earth. Picture gigantic glass mirrors formed without atmospheric contamination, kilometer-wide superconductors cooled effortlessly by lunar light, or fleets of modular megastructures assembled in low lunar orbit, all feeding an economic ecosystem far grander than anything we've known on our single blue planet. It's a vision we've explored across many episodes, from Gardens of the Moon, where we imagine building lush lunar biospheres that transform sterile regolith into living oases, to Moon Mega City, sketching out what happens when a mere industrial park snowballs in the first true metropolis off Earth. Each scenario is a different thread in the same tapestry, asking how humanity will plant its flag, not in conquest, but in creation, on another world. And all starts with simple things: bricks baked from dust, oxygen wrung from the rock, mirrors stretched thin as a whisper to shade or warm the Earth. Each weld and 3D print on the Moon's surface is more than just local industry. It's the opening bell of humanity's transformation into a multi-planetary, multi-habitat civilization. Who knows, maybe soon enough, out of this world won't just be a turn of phrase, it will be a routine work assignment, because the future is not waiting on Earth. Instead, the future will get built on the Moon.